Today we will solve relative motion problems. And as I said earlier, it is not how fast your uncle drives or anything like that. Thank you, Ryan. This occurs on page 95 in the textbook. If you have a textbook, you can join me there on page 95. This will help you with, this will help you with some of the vector stuff that you were struggling with on Thursday. Now, I was away Friday. How did that go? Oh, I think I have some stuff to hand back to you. That's right, I do.
You handed stuff in?
I do. Ryan, this is for you here.
Oh, those things. The
Yes.
one.
Remind me to here.
That thing.
They're right here, yes. Okay, so remind me, some people don't, I didn't get these. The vector handling, I got it all marked. If you didn't do it, you need to get it done. Okay? Remind me to handle that. I want to get going. Okay, so on page 95, join me here. Relative velocities. Now, this always gets a laugh. Tarzan and Tarzana are brawny ape people. I don't know, what kind of visual do you get in your mind when you brawny ape people? Yeah? And are they some sort of like ancestral humans? They're like a part ape, part human? Yeah? Or are they just babies that were raised by apes? Yeah? Just what? And does it matter that they're brawny or not? And what does brawny mean even?
That means they're strong.
Yeah?
That's how they go through vines.
Okay. Well, anyways, they decide to have a race across the river. Both are excellent swimmers and have the same ability. So in other words, regardless of how they race, they're going to get there at the same time because they have the same ability. Ah, yes. Tarzan decides, though, he swims straight across, landing on shore directly across from where he started. Tarzana jumps in and points herself across the river, but ends up farther downstream. So Tarzan tries to go against the current, ends up straight across. Tarzana, she just jumps in and heads straight across. She ends up going downstream. So who wins the race? The two are pictured below in figure 324. Now you guys have that handout there where we start talking about case 1 and case 2, right? So yeah, don't worry about that just yet. So below that it says who finishes first, and we'll get to that.
Where are they racing to?
The other side of the river. But see, Tarzan, he ends up straight across. Tarzana, she ends up downstream. Then there is Cheetah, faithful, brawny ape pet.
Is there a brawny ape pet? Is that even a thing?
Well, I don't know. Is that...
Cheetah, that's me. Okay. It's an ape named Cheetah.
Or is it a dog name because he's an ape pet? Does that mean that he's an ape or that he's a pet of the ape people?
Or it's a chain.
I feel
like it's an ape pet.
I don't know. I think this guy writing it was a little bit... I'll let you fill in the adjective bit. Yeah. I always get a laugh out of faithful, brawny ape pet. And the fact that he's faithful matters too. Pardon me?
Brian Heinbecker.
Yeah.
That's his fault.
This cheetah, though, chose to swim across the same river, but at a time when the floods were raging and the river flowed at 5 times the velocity it did when Tarzan and Tarzana were swimming. Cheetah, too, is a good swimmer and has the same ability as Tarzan and Tarzana.
Drowned.
Did Cheetah finish the crossing in a shorter time? These questions will be answered in the next section. Sounds like a TV show, right? Tune in next week to find out. Yes. Next season, you'll find out about Cheetah, the brave, spotty, faithful, brawny ape pet. Okay. So anyways, let's back up a little bit and let's talk about relative motion. In trying to answer the posed questions, we need to define what relative motion is.
Wait, look at the picture. What is the cheetah?
Can't tell, it's just a...
Look at it.
It's a turtle.
It's a monkey.
It does not look like anything. It's like a weird shape.
Yeah, it just looks like a rag doll kind of thing. Alright, well anyways, moving on to relative velocity. I'm so glad that you're interested in the faithful brawny ape pet. We need to define what relative motion is. Suppose you're traveling in a car and are being observed by a highway patrolman sitting by the side of the road as shown in figure 325. Now, it would be wonderful if this picture was on the same page, but it is not. So if there's two of you, flip one of your pages over so that you can sort of see that picture there. Okay, and you see the cop car here, and there's the policeman, and here is you driving past. Okay, and the police car is stopped. It's at 0, and you are traveling an unwise 140 kilometers an hour as you pass a police car. Have you ever seen that just for laughs? Where the guy's got like a hair dryer and he's pointing the hair dryer at the traffic and people are slowing down? Maybe that was, where did I see that? I don't know.
It would be.
Anyways. So suppose you're traveling in a car and being observed by a highway patrolman sitting by the side of the road as shown in the picture. The patrolman will measure your velocity relative to his position. In this case, the patrolman is not moving. Let's assume the velocity he measured is 140. Your velocity is said to be 140 kilometers per hour east, measured relative to the ground because he's standing on the ground and the ground is not moving. Now, suppose you pass the patrol car with a velocity of 140 while it is moving with a velocity of 100 in the same direction. This is also a bad idea. Do you see that picture on the next page? Okay. So now, the policeman is not standing on the side of the road. He's driving at 100 and you decide to pass him doing 140. You deserve a ticket. And maybe even a psychological exam, because that would be just foolish, right? Okay. While the patrol car has a velocity of 0 in its own reference frame,
Say it again?
I'm just waiting for Heather to finish her text here. This time the velocity is measured 40 kilometers per hour relative to the patrol car. So what's he going to see when you go bombing past him? What's he going to measure your velocity at? Only plus 40. Is he going to pull you over for speeding?
No.
Yes, he's doing 100.
It's only 120.
Okay, but your speed relative to the police car is plus 40. Now, what if you were to turn around
Go that way?
and go this way at 140? What would he register you at?
We're playing chicken now?
He would register you at a speed of
240.
240. Your distance between you is decreasing at a rate of 240 kilometers an hour.
There's no way you catch it.
Right? Does that make sense? Again, also foolish. Now, do the police have to do that mental math? Do they have to get that when they're... No, it all works out. Like they know whether the thing is moving the same direction or towards, and the device does it for them. But this would be relative motion in one dimension, right? Okay, now here's where the book gets really stupid, like it hasn't already. On page 96. So they give names to these vectors. VOG, exactly, is the velocity of the person or object relative to the ground. Okay, so this is a physics professor that likes to, make things harder than they really need to. Do you have on the left-hand side, some kid wrote in something?
Yeah.
You should. You should have VR. So VOG is simply the velocity resultant, or I like to say just the plain old result. We always measure things relative to the ground, unless specifically stated, right? When you go out and you see the speed limit, it says 100 kilometers an hour. It doesn't say relative to the ground, right? Even though we're all traveling faster than that, if you were to observe us, say, from the moon, because the Earth is spinning and traveling through space and blah, blah, blah. Next one is VMG, and it's so small I can barely read it. Is the velocity of the medium the person or object is in relative to the ground. Okay, so that one there, VMG, would be like current or wind speed. It's how fast the wind is going, how fast the river is going. And the last one there, VOM, is the velocity of the person or object relative to the medium it's in. So that, my friends, that last one there, VOM, is like the plane speed or the boat speed. It's how fast Cheetah is swimming. The brawny ape cut.
Wait, Mine says Tarzan.
It could be. Yours could say Tarzan? Yeah. Tarzan, Tarzana, cheetah, all the same. They're all briny, they can all swim the same rate. Does cheetah have clothes on, do you think?
I'm unsure.
Cheetah is an animal. I
I don't know, it's just plain old weird. Okay. So then, you should also have on the left-hand side there, you should also have something like resultant is plane plus wind, or resultant is boat plus current, right? Now, in this case here, we could replace the boat with Tarzan or whatever. Cheetah. Whatever. Okay. So relative motion in one dimension. Let's look at page 97. So this is where that little handout comes in. So in one dimension, the river problem has three possible cases. And I typed out what's in the book. Shown in figure 326. When the river flows, its velocity is 1.0 meters per second east. Tarzana can swim at 2 meters per second. Okay, so there are three possible answers here, three possible cases here, right? So now they make it way harder than it needs to be here, right? So the resultant is Tarzan plus current. If there's no current, well then the resultant is simply 2 meters per second, right? When the river flows, its velocity is 1. Tarzana can swim at 2 meters per second in still water when there's no current.
That's T plus C?
T plus C. No current in the first one, right? It is 1, but case 1 has no current. We're just making it simple for you. Now, in case 2, you're traveling east with the current. So again, the resultant is Tarzana plus current, or 2 plus 1, resultant is 3. They like to use the fancy word collinear. What does collinear mean, do you think? Heather, seriously. Unless Granny's dying, and if she is, then you need to go deal with that and not this. This is not near as important.
Where are we on?
I'm now on page 98.
On our sheet though.
Oh yeah, no, don't you have this?
Are they all separated? Like is that?
No.
Oh, you don't have them separated. My apologies.
We just write our own.
You just have to write your own case 1, case 2,
But are
case
these the separated ones? Like, I don't know, there is cases.
You got it, man.
3. No, we're still on example 7. That's not, we're still here, I'm still here. We're still here. No. That's example 8. Here. Okay, so again, collinear, any ideas? It means in the same direction, in the same line. They share a line, share a direction.
What are you getting the 2 plus 1? Like the 2 meters per second plus 1 meters?
Yep. Tarzana can swim at 2 meters per second. She's swimming east. The current is also east, swimming with the current, 2 plus 1. Relative to the ground.
How are you finding the cases? Like, how do you know the first one there's no?
I'm just making them up. They're in the book.
They're in the book?
They're in the book. I'm now on page 97, says case 1, no current.
That's it.
Flip the page, page 98, case 2, no current east.
Oh,
Okay.
I thought you were just making these up.
Well, I sort of am, but I mean, I'm making them up out of the book. Case 3 against the current. Now, should we write R is equal to T plus C or T minus C? No, let's write plus, because we're swimming against the current. So your speed is actually minus 2 plus 1, so your resultant would be minus 1, right?
Why is it
Because you're swimming against the current, you're swimming west in the opposite direction. This is all basic stuff, right? Like, I mean, really, it's just, we're making it way more complicated than it needs to be. We're sort of laying the groundwork here. Okay, I'm now on example 8, which in the book is on page 99. And they talk about two-dimensional relative velocity, and they go way back to talking about adding vectors tip to tail that we covered in grade 11. Let's go right to the example. So case 1, assume that Tarzan can swim at 2 meters per second, the current is 1 meter per second east. Tarzan is seen to swim directly across. In other words, the resultant is towards the north. Okay, the resultant is towards the north. Now the biggest problem with all these vector questions is the wording is goofy. And sometimes they word it, they give you half of this vector and half of that vector. They are worded terribly. I'm going to try to clean that up on exercises and tests. Okay, but unfortunately we're going to be dealing with what's going on here. So let's draw a picture. That's my result straight across, because that's what it says. Tarzan is seen to swim directly across. How does he do that? Well, he's smart enough to swim against the current at 2 meters per second. The current is like this, right?
Yes.
Okay, so what is the resultant here? Now, most of the time, you're right, r squared equals 1 squared plus the other 1 squared, right? That's not the case here because he's actually swimming the hypotenuse there, right? So in this case here, it's actually t squared is equal to r squared plus c squared. Does that make sense? Why?
Yeah.
So r squared is going to be equal to t squared minus c squared. It's sort of, kind of vector subtraction, but not exactly. Which I understand can cause a great deal of confusion. Okay, we have t squared, it's 2. We have the current, it's 1. So r is going to be the square root of 5, right? What did I just do?
So you just put adding into
Oh, yeah, I did. I knew I made a mistake. 3. Like I said, right? The same way. Tarzan has to know what angle to take. Opposite over adjacent. So opposite would be my C, would be my 1. My adjacent would be my R, which is this 1.7. So he would need an angle of north 30.
Where is theta right now?
Right there.
It's at the bottom of the
Yeah, right in there. So Tarzan would head off at a direction of north 30 west at a speed of 2 meters per second and end up at a resultant of 1.7 straight across. So do you see how it's not really like you've got the direction of the resultant but not the speed, and you've got the speed of this one here but not the angle. So it's a little of both, right? It's confusing, I get that. In example 2, now she swims at 2 meters per second, but she goes straight across. She doesn't try to fight the current. So that is going to look like this, a T again. Well, we were trying to find out the resultant speed. Is what we were trying to find.
So we didn't have to do that.
No, I just threw that in there as a reminder. Is this angle going to be the same? Think so?
Yeah, just the other way.
Yeah?
30 east.
Okay, let's see. Ryan, put the phone away. This time it's r squared is equal to t squared plus c squared. Is she going to end up going faster than Tarzana?
Oh, yeah.
How can you tell?
Because she's
So she's going to go faster? Notice that I've got a different setup here because the r is the hypotenuse, right?
She's going to swim faster, but she isn't going to get, I guess. Depends which way she wants to go. They're trying to both get to the exact same spot.
They're not.
And it's trying to cross. Actually, it shouldn't be the same.
No, it shouldn't be, because you're adding them this time.
It's faster.
They're saying something different there, Anna.
What?
You're not hearing what they're saying, I don't think, or they're not saying what you're hearing.
I'm
Or
talking to myself, mainly.
okay, so her resultant speed is 2.2, and I've heard a few people say, well, yeah, she's swimming faster, and as Riley over here pointed out, she also has to swim farther. So we haven't yet determined who's gotten there first, right? We are interested in this angle here, though. Let's use TAD, opposite over adjacent. So opposite is C, which is 1. Adjacent is my T, which is 2. So it's not 1 over 1.7. It's actually 1 over 2,
0.2. Oh, no, not over 0.2.
which is north 27 east. So it's not the same angle. And if you stop and think about it, I think that'll make sense to you. But the real question is, who wins? Who gets there first? Well, here's how you figure it out.
But no, wait.
What speed does Tarzan have straight across? What's his speed straight across? 1.7. He's swimming that distance in 1.7. The component of Tarzana's that is straight across is actually equal to 2. And this distance is the same as that distance, even though it's not actually a distance direction. So who gets there first? Tarzana. Considerably faster. Tarzan uses up energy and speed doing what? Going against the current. Now, he manages to get across directly. She does what? Ends up downstream. Right? So he's more interested in getting straight across. She says, I don't care, I just need to get across. Right? She's being chased by Cheetah, who is now unfaithful and terrorizing them or something or other, I don't know. Cheetah's relatives or come to rescue he or she. Is Cheetah he or she? I don't even. See?
Female.
It's all very confusing. Okay, so if we talk about Cheetah, remember he's swimming during the times of the floods. So Cheetah goes like this. I'm going to put a big C for Cheetah. Little c for current. Because I got small c for current. I could go CH if you want.
No, it's not the same thing.
No? This big C has this ferocious 8-pet sort of quality to it. Brawny. I would like someone to draw me a cartoon of Tarzan, Tarzana, and their faithful 8-pet, and I'll post it. I'll put it in the slides. Okay, you do it. I'll put it in the slides for next year's semester to look at. Oh yeah, absolutely. Well said there, Deroche. Well said. Your dad would love that joke.
Isn't it?
No, not at all.
Isn't it different if you flip them around?
Cheetah's swimming at 5.
No.
I got it backwards, don't I? Yes.
I mean, it's the same other way.
Yeah, you're right. But
All
for
have the same ability.
you're right. For the sake of correctness, it should be like that. Well done, Matt. So R is going to be the square root of 4 plus to be square root 29, right? 5.4. Now, what about the angle here? Is the angle going to be the same as before? It's going to be a lot greater, isn't it, right? Yeah, exactly right. Okay, opposite over adjacent. So opposite is 5 over 2.
Oh yeah.
I'm looking forward to this, Heather. Are you an artist? Are you? Okay. I was just wondering whether I was going to get a drawing or whether I was going to get like a stick figure. I'll get more than a stick figure? Okay.
That's 68.
68.
Is that actually going to affect our answer or no?
Depends. I never really asked a question here, did I? Right? Yeah. We're just kind of messing around here.
So how do we figure out? If we were figuring out who won, we wouldn't.
If we had to know who won, it would be Cheetah because Cheetah and Tarzana would tie, right? Because Cheetah's component that goes straight across is only 2, and so is hers 2. Right? So Cheetah and Tarzana would tie. Cheetah would just be way farther downstream.
Cheetah would win. He is less riskier. Riskier.
Jonathan?
Say on the left-hand side of the triangle.
Here? CH. Cheetah. Okay, well, let's never mind that. The textbook makes a severe bonehead mistake here in example number 9. Let's have a look at that. This is the one that's a little bit more applicable to what we're going to be doing. If you want to read there about finding the time to cross, you can read that. It's on page 101. They basically say the same thing that I did. Relative velocity involving planes. This is on page 101. A pilot with a heading of north 30 east and an airspeed of 400 kilometers an hour flies into a wind coming from the north at 110. What is the plane's velocity relative to the ground? They're asking for the resultant. And how long would it take to complete a journey at 1,000? Complete a journey of 1,000 kilometers an hour at north 30 east. Well, would the plane end up going at north 30 east? No, because they didn't account for the wind speed, right? So I changed that here. This would actually be, how long would it take to complete a journey of 1,000 kilometers an hour at the resultant angle? Okay, so make that small change. Now, should we draw a picture?
Yeah.
Okay. Should we draw the vectors separately? We've got a pilot with a heading of north or east and airspeed. So what they're giving you there is what?
An angle and the speed.
They're giving you the plane's velocity. Relative to the air means like, if there was no wind, how fast would it be going?
I thought airspeed was like wind.
No, airspeed is how fast relative to the wind. So 400 at north 30 east. The wind is from the north. So it's 110. It's from the north. From the north means
Going south.
going south. Please read carefully. What is the plane's velocity relative to the ground? What are they asking you for? We've got plane, we've got wind. They're asking you for the resultant velocity. If you are on the ground, which direction do you see the plane headed? So is this vector addition or is this vector subtraction? Try again. How do we know it's addition? We're asking for resultant, right? Resultant is plane plus wind. It's subtraction when you're plane or the wind. Exactly. Okay, so vector addition by components, right? North 30 east, just a little sketch here, is going to be like that. And wind is going to be like that, right? So vector addition here. Plane. Plane X, plane Y. PX is going to be 400. This here is 30 degrees. 400 sine 30, right? So it's traveling at 200 kilometers an hour in the xward direction. PY.
How do you know what that is?
400 cos 30. Remember how I like to put my x on the right, y on the left, right? Sort of line them up. Now the wind is straight south. Is there an x component to the wind? There is not. Let's put a 0 there. Is there a y component to it? Yeah, it's all y. Minus 110. Why minus? Have you done the next step? What's the next step? I like to do that just to sort of break it apart. The resultant x is going to be 200 plus 0. And I just show that to sort of, because it's in your notes.
That's confusing. You didn't even listen to my example. No, I wasn't paying attention. Okay, well then don't.
I'm going to write plus 110 to sort of...
Is that 40 or 90? Is that 40, right? Or 46?
346.
Okay.
I'm going to show plus negative 110 to strengthen the description of vector addition here. or to reinforce that, I guess. Okay, what's the next step once you got your Rx and your RY? Put them back together in the triangle, right? Oh, I guess I gotta finish this here. So that's gonna be 236, right? Okay, so 200, 236, does it need to be to scale?
Nope.
Nope.
It's not even possible.
It's not to scale. So, because of the wind, the plane speed is 400, but because of the wind, it's only able to go 309 kilometers an hour at a slightly different angle. What angle does it go at? Opposite over adjacent. I get east 50 north, or this is 50, or this would be 40, right? North 40 east. So the wind knocks it back.
You don't have to know the North 40 East, right?
What's that?
You don't have to know this whole North 40 East thing, right?
Yeah.
Okay. Why?
Yeah.
Why would you do that?
You gotta know the angle,
Why would you do that?
because you gotta know it.
But it was East 50, why wasn't 40?
Oh, it's either the east 50 north and north 40 east are equivalent.
Wait, and why? Can I just say East 50 North?
Yes, but if you said north 40 east, that would be also right.
Oh, I don't like that, okay.
Just the complement of it, the opposite to 9.
I don't like that.
Now, the real question was, how long would it take to complete a journey of 1,000 kilometers at that angle, right? So what angle would they go at? They would go at this angle here. V equals d over t. The speed is 309.3. The distance is 1,000. You're solving for time. And you get like 3.23 hours. Almost 3.5 hours, right? Do pilots have to be able to do this, like with calculators and pencils and papers? No, their plain computer figures it all out for them. But if they end up, without any equipment or any sensors or whatever, yeah, there might be a navigator that actually has to pull out a ruler and do vector stuff and figure it out. They still have to know how to do it. And I would think they would probably have to retest on it on a regular basis. It's not so important if you're flying, like, say, from Chicago to New York or whatever, Toronto to Ottawa, but if you're flying from Toronto to, say, London, England, and you're in the middle of the Atlantic, you kind of want to know what direction you should take, right? Given that you've got limited fuel. Do they just fill up the tanks when they go on a plane ride like that? They don't. You know why? They only take just enough fuel to get there. Well, they don't want to, the more fuel they take, the more weight they have, and so the more fuel they take, the more fuel they have to actually take. They do dump fuel, though, sometimes. If they have to land early, like if you're flying from, say, LA to New York, and there's an emergency, and they have to land, like, in the middle of nowhere, Kansas somewhere, they will dump fuel before they land, because you don't want to dump, they want to land with empty tanks. It's just less dangerous. Okay, I'll stop yakking. On page 103, there's a question, number 2 you can do. On page 116, there's a few more. 35, 36, 41, 42, 43. I have a handout as well. You have the rest of this period. You'll also have tomorrow. I realize that
35 or 25?
35. I think it's just Hannah and Ryan that are away, am I right? Any other band people? Just Hannah and Ryan? Okay, so tomorrow I'll give you a review period as well. Would you like the sort of outline of what you're going to have to be able to do?
Yes.
Did I not do that already for you guys?
Yeah, we did.
Here's what your test looks like. There's DT graph theory. It'll be like, which of the following graphs is forward motion, forward constant motion?
Tell
Or
us what the test is out of.
I'd have to go count it up. I'm guessing 35-ish.
So smallish.
Yeah, well, there will be questions on DT graph theory, questions on VT graph theory, questions on AT graph theory.
What year?
Like, which one of these has a constant negative acceleration? Or which of these graphs, or how would the graph look if it was,
Or like converting them?
yes, or converting, yes. If the DT is this, what would the VT look like? Exactly. Okay? And then they're sort of all together more like that kind of thing. So these you can sort of understand would likely be multiple choice, that kind of thing, right? Then there's basic displacement, velocity, and acceleration theory. Just like knowing about velocity, knowing about acceleration. If I'm accelerating at 2 meters per second squared, what does that mean to the velocity? It means that it's going up by 2 meters per second every second. Stuff that you should know from grade 11.
Oh.
Are you going to be able to study for that? Probably not. Where should you get that stuff if you're if you want to spend some time for that? I'm going to show you here right away. You got this handout way at the start. It says 2.3 velocity on it. You should have got it like on day 1 or day 2. You might want to have a little look through there. Yes, there's a lot of stuff in here.
Is this something that's out of control?
There will be I got simple problem, which will just be like a simple one-step kind of problem. And then there's 2 kinematics problems. I've labeled them type 1 and type 2.
Kinematics, so what's the big formula?
Yeah. Big formula, not Fred and Barney though. It's not Fred and Barney. Like a truck is driving down the highway, it speeds up from 100 to 120 at this rate. How long does it take to get up to the speed? How far does it go? A bit more advanced. Like in that problem pack that I gave you.
Like with those fancy formulas?
With the fancy formulas, that's a good way to put it. There will be, I don't have Fred and Barney here. Maybe that's what this one means. Problem type 2. Type 2 must mean Fred and Barney.
Okay.
Yeah, I think there's 2 of these kind and 1 Fred and Barney. Relative velocities that we talked about today. Okay, the Tarzan and Tarzana. Which one gets there faster? It could be like the policeman on the side of the road. How fast are you going relative to him? Or if he's driving towards you, or... Okay? There will be vector theory, like just basic vector stuff. You will have to add vectors and you will have to subtract vectors. Okay? After the test, I'm going to print this out. You're going to write it. I will have written in here what question numbers these questions were on. Then you will write in your marks and what they're out of. And then you can identify clearly which ones you do and do not get. And then we'll revisit those.
Like you mean after you mark them?
After you mark it, I'll give you this, and you can analyze where your mistakes are. No, I'm going to mark it.
Oh.
Yeah.
I was gonna say, what text that?
Okay, so you'll see this sheet after we're done.